Hello everyone, I am Rajima Dayma. Today I am going to present my poster on household energy consumption analysis, pattern analysis and predictive modeling. Let's start with introduction. My dataset name is homesy.csv. The dataset contains total 5,03,910 rows and 32 columns. The data I collected from Kaggle. The study aims to understand energy usage patterns, evaluate the impact of environmental variables, and develop predictive models for efficient energy management. Here I did EDA, exploratory data analysis, that reveals the target variable house overall does not follow normal distribution. Here I also used statistical testing for normality checking like Anderson-Darling test. The value of Anderson-Darling test is also said that the target variable house overall does not follow normal distribution. So there I used non-parametric test. Here the result shows that when solar energy is available at that time, the electricity consumption is reduces compared to when solar energy is not available. Here I also fit machine learning models such as extreme gradient boost and random forest that provide strong predictive performance, explaining approximately 79% of the variance. Now we will move to the objectives. So the objectives is to analyze whether solar energy reduces household and electricity consumption using statistical testing, to study the effect of environmental variables such as temperature, humidity, and cloud cover, to examine variation in energy consumption across different time periods of the day, to build predictive models for estimating energy consumption, to classify household into high and low energy consumption categories. Research methodology. The study combines statistical and machine learning techniques to analyze household energy consumption. Descriptive statistics for summarize the data, while correlation analysis examines the relationship between the variables. Hypothesis testing such as Mann-Whitney U-test, Kruskal-Wallis test, and Spearman correlation are used to evaluate solar effect, time-based differences, and nonlinear relationship. Additionally, machine learning models including ridge and lasso regression, random forest, extreme gradient boost, and logistic regression are applied to improve prediction accuracy and classify energy consumption patterns. Now, results and analysis. This section presents the key findings from statistical and machine learning analysis of household energy consumption. It includes insight from exploratory data analysis, hypothesis testing, and predictive modeling to understand patterns, relationship, and the impact of factors such as solar energy, weather condition, and time-based variations. Now we can see that the distribution of cloud cover and energy consumption. So the distribution of cloud cover. So we can see that here the data is right skewed and outlier is also present, meaning this suggests that clear weather is more frequent while extreme cloud cover occurs less often. Now we can see that here distribution of house overall energy consumption. So here also we can see that the data is right skewed and high tail. Now the box plot. The box plot also said that the outlier is present and the data is right skewed. So now the temperature and use scatter plot between temperature and use. As temperature increases, use also increases, but sometimes what happen, as temperature increases, use does not increases, meaning temperature and use does not have linear relationship, meaning they both have non-linear relationship, meaning temperature does not influence use. Based on these graphs, the hourly energy consumption pattern shows clear fluctuation throughout the day, with higher uses during morning and evening hours likely due to increase of household activities such as cooking, appliance usage, and occupancy, while lower consumption is observed during midday and late night when activity levels are reduced. The daily pattern further reveals noticeable variation across different days, with certain days exhibiting higher average consumption, indicating that energy usage is not constant and influenced by changing behavioral patterns, lifestyle habits, and external factors such as weather condition. Now, Summarize the model performance. Here I used ridge regression, lasso regression, random forest, extreme gradient boost, and logistic models. This is the type of this model is regression, ML regression, and classification. So the root mean square error of ridge regression is 0.2021, meaning good accuracy, stable model. The root mean square error of lasso regression is 0.2060, meaning slightly lower accuracy, feature selection. Random forest, which is one of the ML regression model. The R square of random forest is 0.79, meaning strong predictive performance. Root mean square error of random forest is 0.482, meaning moderate error, and mean absolute error is 0.282, low average error. Extreme gradient boost. This is also one of the ML regression model. The R square of XGBoost is 0.79, meaning high accuracy best model, and root mean square error is 0.482, similar to random forest. Logistic regression. This is one of the classification model. The accuracy of logistic regression is almost 76%, meaning good classification performance. The receiver operating characteristic score 0.80, meaning strong discrimination ability. Summarize the above table. So here ridge regression shows slightly better accuracy than lasso regression, indicating model stable prediction, while lasso also performs feature selection. Logistic regression achieves about 76% of accuracy with ROC score 0.80, showing good classification performance. Among machine learning models, both random forest and XGBoost demonstrate strong predictive performance with an R-square of 0.79, meaning their RMSE and MAE values indicate moderate prediction error with good accuracy. Conclusion. Household energy consumption shows high variability and skewness. Solar energy significantly reduces electricity usage. Environmental factors have limited but measurable impact. Energy usage is strongly influenced by time patterns and human behavior. Few appliances contribute to major portion of energy consumption. Machine learning models such as random forest and XGBoost provide best predictive performance. Future scope. Future research can focus on expanding the dataset to multiple household and longer time periods to capture seasonal and behavioral variation more effectively. Integrating real-time data through IoT devices and applying advanced techniques such as deep learning can further improve prediction accuracy and support the development of smart, efficient energy management system. Thank you.